There is a stretch of Mooseland Road in rural Halifax County, Nova Scotia, where the countryside looks like much of the eastern shore. Black spruce, damp balsam fir, a gravel turnout, a timber yard, and 2 lanes of asphalt stretching past quiet woodlots. It is ordinary, calm, and utterly unremarkable. Yet just beyond the tree line, out of sight from the asphalt, sits an open pit hundreds of meters wide, where massive haul trucks run around the clock extracting high-grade gold right now in 2026. What makes this place unsettling is not the size of the modern machinery, but the fact that specialists passed over it for generations without grasping what was sitting beneath the moss. How did one of the oldest recorded gold deposits in Canada, sitting in a province almost nobody associates with modern heavy mining, end up hiding the remnant of an ancient ocean floor that arrived from another continent altogether? And why, after more than a century of being worked, abandoned, flooded, and written off, is this ground producing more wealth today than at almost any point in its history? For generations, the conventional wisdom among Eastern Canadian prospectors was simple. Gold belonged to the river gravels of the Caribou, or the deep greenstone belts of northern Ontario and Quebec. Maritime bedrock, by contrast, was assumed to hold only thin, unpredictable quartz veins that would exhaust a family enterprise within a few seasons. That assumption was entirely reasonable in its time. When local gatherers and First Nations travelers traversed the waterways of the Musqueam and Tangier valleys, they knew every outcrop and stream bed, using the waterways as travel corridors long before European survey crews arrived with compasses and chains. When official colonial records first noted gold in the region during the late 1850s, early prospectors treated the rock like a short-term gamble. They chipped out the exposed quartz near the surface, exhausted the visible flecks, and moved on when the water table flooded their shallow shafts. By the late 19th century, early operations along the belt were struggling. The easy surface rock was gone by the 1870s, and the deeper ore was trapped inside dense pyritic slate that standard milling equipment could not efficiently process. Early stamp mills pulverized the rock, but left more than half of the target metal locked in the tailings. Operations opened, lost money, and dissolved into bankruptcy. When local industrial activity collapsed further during the economic shifts of the early 20th century, the workings were abandoned to the forest. Water filled the pits, spruce saplings reclaimed the waste rock, and official provincial surveys filed the location away as a exhausted historical curiosity. What those 19th century miners and early 20th century geologists did not understand, because the fundamental science of continental drift had not yet been established, was the true geological origin of the ground beneath their boots. Nova Scotia's gold does not belong to the ancestral bedrock of the North American continent. It sits inside a vast coastal rock formation known as the Meguma terrane. More than 500 million years ago, long before the Atlantic Ocean existed, this rock was part of an ancient seafloor and volcanic arc sitting thousands of kilometers away near the margin of Gondwana. Hydrothermal vents on that ancient ocean floor spewed superheated, mineral-rich fluids through layers of mud and volcanic ash for millions of years, depositing gold into the soft seafloor sediment. When ancient continents collided during the Tectonic and Akkadian mountain-building events, that entire exotic ocean floor was scraped off its tectonic plate, compressed, and welded directly onto the eastern flank of Laurentia, the ancient core of North America. The gold resting beneath the Halifax County forest was never native to North America. It traveled across a vanished sea on an exotic terrain, crushed and folded into deep slate belts before being buried under younger rock. For most of the 20th century, the true scale of this structure remained invisible. The market price of gold was fixed, the grade appeared too low for traditional underground shaft mining, and the analytical tools required to map fine gold dispersed through deep slates simply did not exist. The turn came when modern exploration geologists stopped treating the site as a series of isolated quartz veins and started evaluating the surrounding slate as a single, massive, low-grade ore body. Modern core drilling and satellite-assisted structural mapping revealed that the gold was not confined to thin surface quartz, but was disseminated throughout vast volumes of host rock extending hundreds of meters into the crust. When international exploration companies acquired the property rights and initiated systematic environmental and geological assessments in the early 2000s, it marked the beginning of a decade-long review process. Establishing a modern open-pit operation meant satisfying strict provincial and federal regulatory frameworks under Environment and Climate Change Canada and the Geological Survey of Canada. By the late 2000s and 10s, modern processing facilities were operational, utilizing closed-loop water management and advanced extraction technologies that turned a forgotten 19th-century prospect into a multi-hundred-million-dollar modern producer. Today, the operation processes thousands of tons of rock daily, with ongoing deep drilling programs continually extending the known boundaries of the ore body. Independent economic assessments estimate the regional impact in the hundreds of millions of Canadian dollars, supporting hundreds of direct technical jobs across rural Nova Scotia. Yet none of this scale is visible from the main road. The landscape hides its history behind spruce trees, quiet stream crossings, and a narrative that written history simply forgot to finish. To understand why this deposit lay misread for over a century, one must trace the deep tectonic assembly of eastern North America back more than 550 million years to the Cambrian period. At that time, the ancient continental core of Laurentia was separated from the supercontinent Gondwana by the Iapetus Ocean. Along the volcanic margins of Gondwana, deep subduction zones drove magma toward the seabed, heating groundwater to hundreds of degrees Celsius under immense hydrostatic pressure. These superheated fluids dissolved gold, iron sulfides, and quartz from deep crustal rocks, carrying them upward toward the seafloor, where they precipitated into layered marine muds and volcanic sediment. Then came the grand tectonic collision. Between 480 and 400 million years ago, during the Tectonic and Akkadian orogenies, the Iapetus Ocean closed completely as continents slammed together. The offshore volcanic terrane and seafloor sediments of the Meguma terrane were violently scraped off the subducting oceanic crust and accreted onto the eastern margin of ancient North America. The immense compressive stress folded thousands of meters of marine slate and greywacke into tight, wave-like structures known to geologists as anticlines. Gold-bearing hydrothermal solutions were squeezed into the structural fractures and crests of these tight folds, forming discrete quartz veins interlayered with dense slate. Eventually, the modern Atlantic Ocean opened during the Mesozoic era, but it broke open along a line further east, leaving the exotic Meguma terrane firmly attached to what is now Nova Scotia. Millions of years of continental weathering smoothed the surface, followed by successive Pleistocene glaciations. The Laurentide ice sheet swept across the region, gouging out deep basins, carving striations into the slate, and covering much of the bedrock under a thick, chaotic blanket of glacial till, boulder clay, and dense spruce forest. For thousands of years, Mi'kmaq travelers moved along the rivers and coasts of this land, identifying outcrops and carrying an intimate spatial understanding of its waterways and mineral resources. When European arrivals began mapping the district in the mid-19th century, they viewed the terrain strictly through the lens of colonial resource extraction. Following the initial formal reports of gold near Tangier in 1858 and along the Musquodoboit drainage shortly after, the Geological Survey of Canada sent field crews to systematically trace the rock formations. Early survey pioneers, including Joseph Howe and later survey geologists like E.R. Faribault, mapped hundreds of kilometers of anticlinal structures across Halifax and Guysborough counties. Faribault spent decades meticulously documenting the folded quartz veins of Nova Scotia, producing map sheets of remarkable detail. His structural model, known as the saddle reef theory, suggested that gold was concentrated almost exclusively in the tight, curved caps of the quartz veins, where the slate layers had pulled apart during folding. This survey model dictated mining strategy for nearly 80 years. Prospectors dug narrow vertical shafts directly down into the quartz veins, extracting the rich, high-grade quartz while ignoring the surrounding slate walls. This strategy created a blind spot that doomed early operations. The gold within the quartz veins was exceptionally high grade, often yielding several ounces per ton, but the veins were thin, frequently less than half a meter wide, and notoriously unpredictable. A shaft could follow a lucrative quartz vein for 30 meters, only to hit a fault offset where the vein abruptly terminated. When underground water flooded the narrow workings or the vein pinched out, companies lacked the capital to drill exploratory drifts through dead rock. Furthermore, 19th-century processing technology relied on heavy stamp mills that crushed the hard quartz to liberate free gold particles through gravity separation and simple amalgamation with mercury. While this recovered coarse gold floating in quartz, it was completely ineffective at capturing fine, microscopic gold locked within the dense, sulfide-bearing slate that encased the veins. Mining syndicates routinely threw millions of tons of slate onto waste dumps, believing it to be barren host rock. By 1912, as fuel costs rose and underground shafts reached depth limits that small boilers could not support, one operation after another shut down. When official provincial archives compiled summaries of Nova Scotia's mineral inventory in the mid-20th century, the Meguma goldfields were written off as exhausted relics of a pre-industrial era. The consensus held that Nova Scotia's gold deposit was too spotty, structurally fragmented, and shallow to support modern industrial mining. But that historic conclusion rested entirely on a fundamental misunderstanding of where the majority of the metal actually resided, raising the question of what modern geochemical science finally saw in those discarded slate walls that a century of geologists had completely overlooked. The shift in understanding began not with a sudden discovery in the field, but in laboratory cleanrooms and through high-resolution geophysical mapping conducted toward the late 20th century. For decades, traditional exploration had relied on manual surface sampling and simple visual identification of visible quartz veins. In the late 1980s and early 1990s, geologists associated with the Nova Scotia Department of Natural Resources and independent exploration groups began systematically re-evaluating the historical mine archives. They pulled 19th-century hand-drawn cadastral maps, old underground level plans, and provincial survey sheets, cross-referencing them with newly acquired regional datasets. The first major breakthrough came from airborne magnetics and electromagnetic surveys. When low-flying survey aircraft towing sensitive cesium vapor magnetometers swept over the dense forest cover of eastern Nova Scotia, the instruments picked up subtle magnetic anomalies running parallel to the regional folding. These geophysical readings traced iron-rich slate units and deep-seated structural shear zones that extended far beyond the small, localized quartz pits shown on Victorian survey sheets. The rock units were not isolated, disconnected pockets. They were continuous, regionally extensive structural corridors. To confirm what lay beneath the glacial drift, field teams brought in diamond drill rigs equipped with wireline core barrels, extracting continuous cylindrical rock cores from depths exceeding 500 meters. When researchers subjected these drill cores to fire assaying and inductively coupled plasma mass spectrometry, the chemical analysis revealed a shocking signature. The quartz veins were indeed rich, but the surrounding slate wall rock, long dismissed by 19th-century operators as barren waste, contained consistent, low-grade gold mineralization measured at 1 to 3 grams per ton, spread across widths of tens to hundreds of meters. Subsequent microscopic analysis using scanning electron microscopy and electron probe microanalysis revealed why generations of prospectors had missed it. A significant fraction of the gold was submicroscopic, existing as invisible native particles measuring less than 10 microns across, tightly bound within the crystalline lattices of arsenopyrite and pyrite grains embedded throughout the slate. 19th-century stamp mills had simply washed these microscopic particles straight into the tailings ponds, unable to liberate gold that could not be seen under a standard hand lens. Further geological validation came from airborne laser scanning, or LiDAR. By firing millions of laser pulses per second from an aircraft through the dense canopy of black spruce and balsam fir, geomorphologists generated precise digital elevation models of the bare Earth surface. The LiDAR imagery stripped away the vegetation cover, exposing subtle topographical expressions of ancient fault offsets, anticlinal fold axes, and previously unmapped historical trenches cut by Victorian prospectors over a century ago. When combined with regional soil geochemistry, tracing pathfinder elements like arsenic, antimony, and tungsten through glacial till samples, the full geometry of the deposit finally snapped into focus. It became clear that the historical miners had been picking at the edges of a massive, bulk-tonnage gold system. Where 19th-century syndicates saw a collection of precarious, narrow underground veins that were too expensive to chase past the water table, modern analytical science proved the existence of a continuous, broad ore body suitable for open-pit extraction. The physical rock had not changed at all, but the analytical tools used to interrogate it had completely rewritten its economic map, setting the stage for a massive transformation of the surrounding countryside. The re-evaluation of this rock has transformed local geography from a quiet, rural backwater into an industrial center of major regional significance. But that transformation comes with concrete physical consequences. Where 19th-century prospectors left scattered, moss-covered pits and rotting timber shoring, modern open-pit mining carves out excavations covering hundreds of hectares. Massive quantities of slate and greywack are blasted, hauled, and crushed daily. The sheer volume of material movement requires heavily engineered infrastructure, from reinforced haul roads to specialized processing mills operating under environmental licenses monitored by Nova Scotia Environment and Climate Change. Water management is the most critical technical challenge on site. The host slates are rich in iron sulfides, primarily pyrite and arsenopyrite. When exposed to oxygen and rainwater during large-scale excavation, these minerals run the risk of generating acid rock drainage, potentially leaching metals into local watersheds. To prevent historical contamination patterns from repeating, modern operators must construct lined tailings facilities, water treatment plants, and real-time hydrological monitoring stations. Millions of Canadian dollars are invested annually in closed-loop water treatment systems designed to neutralize effluent before it enters surrounding drainage networks. The economic footprint is equally substantial, though it requires precise breakdown to understand what the numbers actually represent. Total capital investments for modern site development and ongoing expansion projects frequently exceed 300 to 500 million Canadian dollars. Independent economic studies project cumulative direct and indirect output across Nova Scotia in the hundreds of millions, supporting hundreds of full-time technical jobs, from heavy equipment operators and process engineers to environmental monitoring specialists. Yet these large headline numbers must be viewed within context. A significant portion of capital expenditures covers imported heavy machinery, fuel, specialized processing chemicals, and regulatory compliance costs, rather than circulating directly into the immediate municipal economy. Furthermore, the legal and regulatory framework surrounding surface and mineral rights in Nova Scotia differs markedly from other jurisdictions. Under provincial mining legislation, surface ownership and mineral rights are severed. Crown minerals belong to the province, requiring exploration companies to acquire mineral claims through Nova Scotia's Registry of Mineral and Petroleum Titles, while negotiating surface access agreements directly with landowners. Unlike 19th-century claims that were staked with wooden posts and recorded in local courthouses, modern properties are defined by precise digital cadastral grids maintained by provincial surveyors. What remains unresolved is the long-term environmental and structural legacy once active production eventually ceases. While current operations are legally mandated to submit comprehensive closure plans and post financial assurance bonds running into tens of millions of Canadian dollars to cover future land reclamation, post-mining landforms remain permanently altered. Deep open pits eventually fill with water to form pit lakes, while covered waste rock storage facilities require perpetual monitoring to ensure acid generation remains suppressed for decades. As exploration teams continue to sink diamond drill holes deeper into adjacent fold structures, the resource estimates continue to evolve. Every new core barrel pulled from the slate adds to a geological model that grows larger rather than smaller, proving that the earth beneath rural Halifax County holds secrets far vast than Victorian prospectors ever imagined. Yet as operations push further into the bedrock, a broader question emerges about how an entire region forgot its true origin. The story of Nova Scotia's Meguma gold belt reaches far beyond a single open pit off Mooseland Road. It points to a structural pattern that repeats across the entire eastern seaboard of North America. What appeared to 19th-century miners as a few scattered quartz veins was actually a single, continental-scale structural system stretching from the southern Appalachians through the Maritimes and into Newfoundland. The anomaly did not hide behind a secret or a fence. It hid behind an intellectual assumption, the belief that gold could only exist in high-grade quartz veins because early stamp mills had no way to capture anything else. What kept this immense mineralized belt effectively invisible for more than a century was not a lack of physical evidence, but a geological taxonomy that mistook the container for the contents. Geologists looked at the quartz because the quartz was visible to the naked eye, while ignoring the millions of tons of slate that wrapped around it. By defining gold mining strictly through the narrow technology of 19th-century shaft sinking and gravity mills, Early industry professionals established an official narrative that outlived the mines themselves. Once that narrative was published in government survey bulletins, it became an accepted truth that passed down through generations of exploration maps. Even now, the full story of the Meguma terrane is far from complete. Geological Survey of Canada researchers and university teams continue to investigate the exact pressure and temperature conditions that drove gold-rich fluids into the slate during the Acadian collision 400 million years ago. Geochemists are actively studying how fine gold behaves in post-glacial soil profiles across the Atlantic provinces, attempting to trace covered ore bodies that sit beneath deep glacial overburden. Vast stretches of the slate belt remain completely unmapped at high resolution, hidden beneath muskeg, coastal lakes, and dense boreal timber. The map printed in atlas volumes looks neat, fixed, and settled. The solid ground beneath it is still moving, still settling from the weight of vanished glaciers, and still holding exotic pieces of ancient continents that arrived from across forgotten oceans. Which landscape anomaly or forgotten mining site in your own province or territory has always made you question what sits beneath the surface? Tell us about it in the comments below, and consider subscribing to stay connected with our ongoing investigations into the hidden geography beneath our feet.